So hello students, let us discuss about the construction of the character table in this presentation. So before going into that, let us just have an idea about the Great Orthogonality Theorem, which is going to help us uh, to construct the character table. So the Great Orthogonality Theorem, mathematically, it is represented by the following statement, mathematical statement. So Great Orthogonality Theorem, which is one of the theorems of representative theories, which will be stating that all the symmetry elements will be orthogonal with each other. So the mathematical statement will be, okay, so it will be the summation over R, the symmetry elements, which will be the summation of the irreducible representation, ith irreducible representation, R, M, N. It is the summation of the product of two irreducible representations, elements of or characters of two irreducible representation, which will be equal to h pi square root of Li, Lj. Then comes the Kronecker delta Ij dot M dash, Kronecker delta N dash. So this is how the mathematical statement, which is actually given over here. Okay, so this you can underline and for your memory. Okay, so now let us get into the terminologies that we have to know about from this mathematical statement. So what are these terms? Where I and J, okay, so they will be the irreducible representation. Irreducible representation. Then what will be the H that we know already? It is the order of the group order. Okay, so that is the number of the symmetry elements or operations. Then comes Li, Lj. So it is the dimensions, okay, irreducible representations, dimensions, okay, so dimensions. Then comes R. So R here it is representing the various symmetry elements of a group, various symmetry operations, otherwise symmetry elements of a group. Then comes the irreducible representation. Here it is representing the element which will be present in the mth row and nth column of an ith irreducible representation. Okay, so let us be familiar with all these things. The next M dash, N dash, again this will be the element in the mth M dash the row, then N dash the column belonging to jth irreducible representation. So you know very well the character table. Here it comes like this, the character table. So where you could find okay, so here you have the point group here, point group. Okay, so here it comes the symmetry elements or symmetry operations. Okay, fine. Then here it comes all irreducible representations. Okay, so here is the point group. For example, if we are representing C2V point group, what are the symmetry elements in point group? That is C2V point group. It will be E, C2, sigma B XZ, and then sigma B YZ. So all these are represented to be the symmetry elements. So this is what the character table, and whatever here you have the elements A1, A2, sorry, B1, C1, D1, like that. So like that to B2, C2, T2. Now here the element which is in the mth row and the nth column of ith irreducible representation. If you take this to be ith irreducible representation, then this will be in the mth row, okay, and nth column. This is what it is represented. And if this representation, irreducible representation, is considered to be jth irreducible representation, then the m dash the row and n dash the column will be this one. So this is the element represented over here. Then what will be the order? 1, 2, 3, 4. So how many symmetry elements you have? 1, 2, 3, and 4. So H will be the order over here. Okay, the dimensions will be the irreducible representations belonging to identity. So whatever the character comes over here, then that will be the dimensions of that particular uh, representation, irreducible representation. Okay, the dimensions. If it is 1 over here, then it is one dimensional. If it is 2, and the 2 will be the character for the identity for a particular irreducible representation, then that will be 2 dimensional. So like that. So all this will be discussing in future when we construct the character table. Hope you understood up to this one. Yeah. Okay, then what about this one? Kronecker delta. So this is said to be the symbol M, M dash, N, N dash. So here they are called as Kronecker delta. Okay, which will be usually having the values 0 and 1. Now, based on this, the main theorem can be made into 3 similar equations. So we have 3 similar equations, and let us see the conditions. So based on that, 3 similar equations have been listed over here. That is, when the irreducible representations I is not equivalent to irreducible representation J. Both are different, and I is not equal to J, then the Kronecker delta I, J will be equal to 0, and the other condition will be M is equal to M dash and N is equal to N dash. So the elements will be belonging to the same group of different irreducible representation. So here the relation can be given in this way, that is the equation out of the theorem, it can be represented like this. So summation over R, it is the product of irreducible representation R, M, N, then irreducible representation J, Jth irreducible representation, the element M dash, N dash, star will be equivalent to what? 0. So what do you mean by this one? So let it be second relation, and above 1, let us number that to be the first relation here. Okay. So the second relation. So here, what does it mean? The elements of corresponding matrices. Okay. The elements of corresponding matrices. Corresponding matrices means here in this case belonging to the same group, means the matrices belonging to the same groups of different irreducible representation. Irreducible representations are orthogonal. Okay, so in this case, what you say here, okay, so here we have irreducible representation I, irreducible representation J, then if it is E, okay, so here the same groups element, this one and this one, of different irreducible representation are orthogonal. So here A1 and A2 we say both will be, if you do this summation of this product, then we will be, that will be equivalent to what? Both will be orthogonal with each other. So this is what it is represented in this equation. Okay, then the second equation, here it comes like this. So when here irreducible representation I is equal to J and I J are equal, in that case Kronecker delta Ij will be equivalent to 1, but the condition M should not be equal to M dash. Both are different. N should not be equal to N dash. Okay, so both will be different. So here the relation will be, so summation over R, irreducible representation R Mn. Okay, so here it will be irreducible representation. Again, here we can represent it as R. I means same irreducible representation since both are considered to be same. Okay, then here it will be M dash N dash star equal to 0. Now here what is it? What is this? It is representing the elements of matrices. Okay, the elements of matrices which will be of different sets of matrices which will be belonging to the same irreducible representation, of the same irreducible representation or orthogonal. So here in this case, if we are taking, for example, So this will be irreducible representation I. In this case, I and J both are equal. Then if we are talking about if it is C to V, E will be there, C2 will be there, sigma V X is Z, sigma V Y is Z. So in that case, the elements of different sets of the same irreducible representation, A1, B1, C1. So likewise, A1 and B1 will be orthogonal with each other, which will be of same irreducible representation. You need to consider the elements, then the product of that will be orthogonal. So this is what the third equation represents, so which has been derived from that theorem. So from equation 2 and 3, so let us just consider this to be 3. So what it is derived, or what it could be concluded. So from equations 2 and 3, okay, so what is that? The sum of the products of the irreducible representation is equal to 0. Okay, so which is actually representing Great Orthogonality Theorem. Okay, so this is how. Then one more relation also can be derived, one more equation. So the third relationship from the above equation, the condition when I is equal to J, M is equal to M dash, N is equal to N dash. So in that case, what will happen to the equation? So it will be summation over R, and the product of the irreducible representation, ith irreducible representation R, Mn. Then here again, I is equal to J. So here we can represent by I. Since M is equal to M dash, N is equal to N dash, here again we are going to represent Mn star will be equivalent to what? H divided by Li. Okay, so here we have actually H divided by square root of Li Lj. If Li is equal to Lj, then that will be Li is equal to Lj, means Lj will be equal to Li, then Li square will be Li here. So this is how here we have got H by Li. Then comes Kronecker delta. Okay, so in this case, Kronecker delta Ij equal to Kronecker delta Mn equal to M dash, Mm dash N dash will be equivalent to what? 1. So here this is another relation. Okay, so this can be another relationship that we have derived from that theorem. So these are the three conditions. So based on these theorem, we can derive actually 5 rules. Okay, we can actually derive 5 rules based on this, and making use of these 3 equations, and we get 5 rules about this irreducible representation of a group and their character. So 5 rules out of these 3 relations are derived okay, which is going to be used for the construction of the character table, okay, which is used to construct the character table. Okay, so let us discuss about the construction of the character table. Okay, before discussing that, what are the 5 rules? Let us just see the 5 rules. So, based on the above theorem, the 5 rules out of these 3 relations or the theorem have been derived, and this will be much helpful for the constructions of the character table. So here the important properties of the irreducible representation are indicated by these 5 rules. So what is that 5 rule? So the number of irreducible representation in a group will be equivalent to number of classes in a group. So this is the first rule. So in this case, if you are taking a character table, C2V, E, C2, sigma V, XZ, sigma V, YZ. Okay, so here how many symmetry elements are there? 1, 2, 3, 4. Or how many classes are there? 1, 2, 3, 4. 4 classes, then you have 4 irreducible representation. So that is the meaning for the first rule. How many classes will be there? That many irreducible representation will be there. For C3V, we have E, 2C3, 3 sigma V. So we have 1, 2, 3 classes, and equivalent to that we have 1, 2, and 3 irreducible representation. So this is the meaning for rule 1. So rule 1, number of classes that will be equivalent to number of irreducible representation. So this is the first rule. Then the second rule, the sum of the, here comes the sum of the squares of the dimensions of the representation will be equal to order of the group. So again I am repeating, the sum of the squares of the dimensions of the representation will be equivalent to the order of the group. So what does it mean? So let us just see from that a representation. Okay, so the dimensions, sum of the second rule, it is the sum of the dimensions of the representation will be equivalent to the order of the group. Okay, so the dimensions are usually said by the dimensions or represented by the characters of, dimensions are nothing but the characters of E, that is the chi of E. Okay, the characters of E. So which is the character of here? Here if it is L1, L2, L3, L4, then summation of the sum of the squares. Okay, here the sum of the squares of the dimension, the sum of the squares of the dimensions, then if you do that, then that will be equivalent to what? Sum of the squares of the dimension. So L1 square, L2 square, L3 square plus L4 square, and that should be equivalent to what? H. Similarly here L1, L2, L3, then here it will be L1 square, L2 square plus L3 square is equal to what? H. So for this C3b, what will be the H value? H is the order. So H order is represented by H. So in this case, H is equal to how many symmetry operations are there? 1E, 2 C3s and 3 sigma V. So we have how many symmetry operations? 1E, 2C3, 3 sigma V. 3, 4, 5 and 6. What about here? The order here for C2V, all individual symmetry operations E, C2, sigma V XZ, sigma V YZ. So 1, 2, 3, 4. 4 symmetry operations are there. So this is what then here it is supposed to be equivalent to, it is supposed to be equivalent to here 4 and here it should be equivalent to what? 6. Then we have to evaluate what could be L1, L2, L3. So that will be seen during construction. So this is what the second rule says. So what is the third rule then? The sum of the squares of the characters in any irreducible representation is equal to what? H. Again, I am repeating, the sum of the squares of the character in any irreducible representation is equal to H. Say for example, if it is A, B, C, D are the characters of any irreducible representation, then the sum of the squares of those characters should be equivalent to what? H. So let us just see about that one. So let us see the representation in a similar way as it is represented here. Okay, so what is the third rule? Actually, the third rule says that the sum of the squares of the characters in any irreducible representation or in an irreducible representation should be equal to what? H. So in that case, let us take an example of first irreducible representation, which will have the character A1, B1, C1, D1. So in that case, it will be A1 square, plus A2 square plus, A1 square plus B1 square plus C1 square plus D1 square, then that should be equal to what? H. So this is what the third rule says. So by solving this, we will be able to find the characters of any irreducible representation, and rest of the elements whichever here, it can be found using the fourth rule. So how it is done and what is that fourth rule says, let us see. So what is fourth rule? It is representing the vectors whose components, are the characters of two irreducible representation are orthogonal. That is, the characters of two different irreducible representations, if you are taking, which belong to the same group, then that will be orthogonal to each other. Say for example, A, B, C, D are the characters of ith irreducible representation, A dash, B dash, C dash, D dash or of jth irreducible representation. Then the product of the characters of the same group, the sum of the products of the characters of the same group should be equal to what? 0. That is, they are orthogonal. So in this case, let us just see. Here it will be first irreducible representation A1, B1, C1, D1, and the second irreducible representation, let us denote by A2, B2, C2 and D2. So what is the fourth rule? the characters of the two irreducible representation belonging to the same group are orthogonal. That should be equivalent to what? 0. Okay, let us see that. Then in that case, so this is the third rule. Then what is the fourth rule? A1 in A1, A2 plus B1, B2 plus C1, C2 plus D1, D2 should be equivalent to what? 0. It should be equivalent to 0. So this is what the fourth rule says. By doing this fourth rule, let us or we would be able to evaluate the characters of other irreducible representation. Okay, so these are the steps that has to be followed, or rules that will be used in order to find the characters of the irreducible representation of a particular point group. Okay, so and the last rule says that in a given representation, any irreducible representation, the characters of all the matrices belonging to operations in the same class will be identical. So this is whatever the character that you find here, if it is 1 over here, then all the symmetry operations of this particular class will be having the same character. If it is 2C3, it is nothing but C31 and C31 and C32. So both will be having the same characters. So this is what the last rule actually says. So applying these 5 rules, we can develop the character table for various point groups. Okay, so let us discuss that in the next session.